Hello friends, in this video let us discuss about the working principle of DC motor. So any electrical motor in general terms can be defined as an electromechanical device which converts the energy from electrical domain to mechanical domain. So similarly your DC motor in simple words is a electromechanical device which converts the direct current, that is DC direct current DC into mechanical energy. So this is your DC motor. So it is of vital importance in industries and it is equally important for the engineers to understand the working principle of DC motor. Now before going to the working principle of DC motor, let us see the very basic construction of your DC motor. So the DC motor contains a armature conductor. So this is your armature which is connected to the supply end. Let us say I am having a battery, DC battery, and my current is flowing from here, and the armature conductor is connected to the supply end through the commutator segments. So these are your commutator segments, this part and this part, and these two parts are your brushes. So the armature is connected to the supply end through the commutator segments and brushes, and the whole armature conductor is placed within the south and north poles of a electromagnet or permanent magnet. So this is your south pole and this is your north pole. Now going into the details of operating principle of your DC motor, we should have a clear understanding of what is Fleming's left hand rule. So Fleming's left hand rule gives you it determines the direction of force being experienced by a current carrying conductor. Fleming's left hand rule, that you can say FLR. So if I am having a magnet, let us say this is a magnet and here is my north pole and this is my south pole, and similarly I am having other magnet which is having south pole here and north pole here. Now if I place a current carrying conductor perpendicular to the magnetic field, that is uniform magnetic field here, if I am place a perpendicularly the direction of current in this conductor, if I say this is my conductor and the current flowing is in this direction and this is my magnetic field direction. So when a current carrying conductor is placed in a magnetic field and where the magnetic field is perpendicular to the direction of current, then this conductor experiences a force which is mutually perpendicular to both the direction of current and the magnetic field. So if I stretch my index finger, middle finger and thumb of a left hand in such a way, if I say this is my current, this middle finger represents my direction of current and this finger represents my armature, that is the magnetic field, then the thumb finger represents my force. So the force is acting upward direction, this is my force. So if I say this is my current and this is my magnetic field B and the force experienced is upwards, that is the force being experienced by your conductor is given in by this thumb finger. Just the way to remember is FBI. F for force being experienced by the conductor, B for the uniform magnetic field and I for the direction of current. So FBI, the best way to remember your Fleming's left hand rule. Now we have found the direction of force being experienced by the conductor. Similarly we can determine the force. So if you see here, you can see the direction of magnetic field. So this is flowing from north to south, a uniform magnetic field exists. This is your B and this is your current. So current is flowing here I. If I say I current is flowing, then the force being experienced by this conductor will be mutually perpendicular to both the current I and B. So in this way, Fleming's left hand rule helps in determining the direction of force being experienced by your conductor. Now, to have a clear understanding of the working principle of your DC motor, let us determine the magnitude of force being experienced by the armature conductors. So we know that when an infinitely small charge, let us say dq, if I say here a infinitely small charge dq is made to flow at a velocity v under the influence of both magnetic field B and electric field E, then the force being experienced by this charge, that is given by dF, that is the Lorentz force, is equal to Q into E plus V cross B. So if I say my magnetic lines, these are my magnetic lines, and this is I am having a current carrying conductor I in this direction, and this is my magnetic field B, then due to the short element, let us say dl length of the conductor, and this is your di, then the force being experienced by the charge dq is given by q into E plus V cross B. This is your, you can write dq. So now for considering the operation of motor, you are having your electric field E is equal to 0, therefore I can have dF is equal to dq into V cross B. So it is a cross product of the velocity of the charge, that is a dq, and it is across magnetic field. So cross product of velocity and magnetic field. So I know the velocity can be of the charge dq can be given by the length of the conductor carrying charge, dq is dl upon dt. So the velocity is given by the dl by dt. dt is the rate of charge, that is the rate of charge dq flowing through this length dl. So you can write here dq into dl by dt cross b. So from here dq by dt is given by the current, that is I, so I dl cross b. Now I can write it as force is equal to L into I cross B. Now here this is the angle between the current I and the magnetic field, that is theta. So as these are cross products, then I can write it as LIB sin theta. So I know my A cross B can be given by AB sin theta. Similarly, I cross B can be written here as IB sin theta. So this is my force, that is the magnitude of force being experienced by a charge dq. So here V is the velocity of the charge, and it is given by dl by dt, where dt is the time for being the charge flowing through the dl length of the conductor. So now if I look at the position of armature, then I am having a current flowing at the left hand side of my armature is I, then at the right hand side of my armature is minus I. So this is because of the fact the currents are flowing opposite with respect to each other. So with respect to this current is flowing opposite. So with respect to this current is flowing opposite. So now the construction of DC motor at this position is such a way that at all instants the direction of current is always perpendicular to the magnetic field and so the direction of current is always proportional to the magnetic field. So therefore the force, you can say the direction of force being experienced by the armature conductor is always perpendicular to the current carrying conductor, that is the direction of current and the magnetic field. So we can have a force being experienced by like this here and here in this direction. So this is your force. So this is your force. So nothing but here the direction of force is mutually perpendicular to both the direction of current and the magnetic field, and here at this position the force being experienced by the armature conductor is always constant, because the armature conductors are arranged in such a way that the armature conductors, the direction of current is always perpendicular to the direction of magnetic field. So this is your direction and this is your current. So the force being experienced by the conductor is always mutually perpendicular to this direction of current and the magnetic field, and hence it is a constant. That means you are having a theta is equal to 90 degrees. Therefore you can have the force being experienced by the conductor is given by BIL. Now if I say the force being experienced by this conductor, that is the left hand side of conductor, can be given by B into I into L. Similarly, the force being experienced by the right hand side of my conductor can be given by force is equal to B minus I into L. So this will be minus BIL. At this position you are having the two forces which are equal in magnitude but opposite in direction are the two sides of the armature. So since I know the distance between the two conductors can be given by some distance W, let us say some distance W, which is the distance of this armature turn. So now as the two forces are opposite in direction and equal in magnitude, this results in a rotational force or a torque, so that results in the rotation of your armature. Now let us find the expression of torque, for an angle alpha that is created by the armature turn with the initial position of the armature. So if I say the torque is given by the force that is acting in the tangential direction of rotation of your armature, force that is tangential into the distance, that is the armature distance, that is, or you can say the distance between the two forces is given by W. So therefore I can have my torque is equal to, so if I say this is my force and if my direction of rotation of armature is in anti-clockwise direction, then the tangential force being acting on this armature conductor will be given by the force into cos alpha, that is F cos alpha. So we know the alpha is the angle between the armature turn, that is the plane of armature turn, and the initial position of armature. So if I say this is your armature initially, and after some angle it is going to create some turn like this. So the angle between the reference position of your armature and the later position of your armature is given by the alpha, so it creates a term cos alpha. So I can write here F cos alpha into W. So I know from here my F is given by BIL, therefore I can write torque is equal to BIL cos alpha into omega. So the cos alpha term in this equation very well signifies that unlike force, the torque is not same at all positions. So the torque keeps on varying as you change the alpha. So let us do a step-by-step analysis how the torque is going to change and the principle behind rotation of this motor. So if I go to the step 1 I am having the armature at the same position, that is the armature conductor here placed in the north-south poles of a electromagnet or permanent magnet, and the direction of current is perpendicular to the magnetic field, and at this position I am considering my alpha to be 0, that is the reference position of my armature. Therefore at this position I am having my torque, that is BIL cos 0 degrees into W. So this will gives me BIL W. So since the alpha is 0, therefore and for alpha is equal to 0, my cos 0 is equal to 1, that means I am having a maximum torque at this reference position of my armature. So this maximum torque helps in overcoming the inertia of rest of your armature and makes it to rotate. So definitely we need this maximum torque to overcome the inertia of the initial inertia of rest of this armature. Now as you turn, so this is the initially this is the position of your armature and this is experiencing a force in this direction, and as you keep changing as you keep turning your armature, let us say it has turned to some angle alpha and the force in that direction is given by F cos alpha as we did here. So as your alpha keeps on increasing and finally the last position of the alpha will be going to 90 degrees. So from the 0 degrees to 90 degrees, where alpha, as it goes from 0 to 90 degrees, the cos alpha term decreases. So as the cos alpha term decreases, the torque being experienced by your conductor also decreases. In your step 2, as you see, as alpha increases and goes to alpha is less than 90, the torque will be decreasing. So the torque will be decreasing and it will be less than VIL into W. As we know that as alpha is increasing, the cos alpha term decreases. Now in the step 3, if you see, in the step 3, what happens is a point is reached where the armature conductor is exactly perpendicular to the reference position of your armature. That means it becomes like this, exactly perpendicular. So if you flip this 90 degrees to the reference position, so this turn will be going into the board and this will be coming out of the board. So at the 90 degrees position, what we are having is, as alpha is equal to 0, my cos 90 gives me 0, so the torque will be 0 at this position. So, but the armature conductor do not come to a standstill position because the DC motor, the operation of DC motor has been engineered in such a way that the inertia of motion of this armature conductor is just enough to overcome this null torque, that is at the point of 90 degrees. So this is a great advantage, and the engineered in such a way that the inertia of motion of the armature conductor is just enough to overcome that null torque, and such that your armature conductor won't come to a standstill position. Now from when it crosses the point 90 degrees, in your step 3, when it crosses the point 90 degrees, so again your alpha keeps on decreasing. So as alpha keeps on decreasing, the cos alpha keeps on increasing, and hence your torque again starts to increase, and when it comes to again the reference position, you are having a maximum torque again. So this keeps on continuing throughout the circle, and in this way the DC motor keeps on rotating. So this is all about the working principle of DC motor. So here we have understood what is the Fleming's left hand rule, and we have understood what is the Lorentz force, and we have understood what is this cos alpha, and due to this term cos alpha, our torque keeps on changing unlike force, and we have understood stepwise as angle is changing how the torque is going to affect it with the angle, and we have seen how the null torque is being overcome by the inertia of motion of the armature conductor at the angle of alpha is equal to 90 degrees, and we have seen the principle of rotation of the motor, principle of rotation of this armature conductor within the south pole and the north poles of a permanent magnet or electromagnet. So I hope you have understood well. Please subscribe to the channel. Thank you.